Hello everyone, welcome to another episode of Math-221. So today we're going to finish up with section 7.2 and then we will cover section 7.3 and 7.4. Okay, so let's continue section 7.2, which was on one-to-one and onto and inverse functions. So last time I started showing you how to do the proofs of one-to-one and onto, and I'm going to do some more examples of that this time and finish that up, and that is what your quiz will be on, so it's important to understand this. Okay, so let's just review what one-to-one means. So we say that a function big F from big X to big Y is one-to-one if and only if for all little x1, little x2 in big X, if big F of little x1 equals big F of little x2, then little x1 equals little x2. So in other words, the same output means that you had the same input. That's what that's saying. And then a function big F from big X to big Y is not one-to-one if and only if there exist elements little x1 and little x2 in big X, with big F of little x1 equals big F of little x2, and little x1 and is not the same as little x2. So this would be saying same output, but different inputs. Okay? And then the way that you prove that something is one-to-one is first you suppose that little x1 and little x2 are elements of the domain big X, such that little x1 and little x2 have the same output from the function. And then you show that that implies that little x1 must equal little x2. And then to show that the function is not one-to-one, you simply have to find some elements, little x1 and little x2 in big X, so that they have the same output, but they were not the same inputs. So let's go over some examples where we do that. But before we go over examples, let's review what onto means. So onto, if you have a function big F from big X to big Y, that is called onto if and only if for all little y's in big Y, there exists a little x in big X, such that little x, when you plug it into the function, gives you little y. So this means for every possible output, and by possible output what I mean is everything in the codomain, there is an input that produces it. So basically we reach everything in the codomain. And then to show that a function is not onto, you have to show that there exists a little y in big Y, so there exists something in the codomain, such that for all little x in big X, so for all elements in the domain, f of x does not equal y. So that means there is no, so there is something in the codomain that is never output by the function. Okay? And then the way you do that, the proofs is, so if you're proving that something is onto, you suppose that little y is an element of big Y, and then you show that there exists an element, this is supposed to say little x, not big X. You show that there is an element little x of big X that produces y when you plug it into the function. And then to prove that that f is not onto, what you have to do is find an element little y in big Y such that little y does not equal f of x for any little x in big X. And so usually this part here, you prove this by contradiction. So you suppose that you can produce little y, and then you show that leads to a contradiction. Okay, so let's go over some examples. Okay, so let's go over some examples. When I was looking at the textbook, I found that the homework problems in the textbook were not really adequate for what I wanted to go over. So I've made up some examples that are not from the textbook, and I've also made up some homework problems that are not from the textbook. So I put the solutions for those homework problems on Blackboard on today's post on the handouts and homework page. Okay, so let's go over this one. So I'm defining little f from the real numbers to the real numbers. So the codomain and the domain are both the real numbers by this rule here, f of x equals 2x cubed plus 1. And first I'm going to prove that f is 1-to-1. Okay, so what I need to do is I'm going to pick two elements in the domain, and I'm going to suppose that they produce the same output. So in other words, I suppose that f of x1 equals f of x2. So you always start this way when you're proving that something is 1-to-1. And then your goal is to show that x1 must equal x2. Okay? So it's actually pretty simple to do it. So because f of x1 equals f of x2, that means, so now you're just going to use the formula for the function. So that means that 2x1 cubed plus 1 equals 2x2 cubed plus 1. All right, and then you just work with this equation until you get x1 equals x2. So I'm just going to eliminate the 1 on both sides, so then I get 2x1 cubed equals 2x2 cubed, and then I'm going to cancel the 2's on both sides. So now I have x1 cubed equals x2 cubed, and then I'm just going to take the cube root of each side. Okay, and then I have x1 equals x2. And at this point you're done and you can stop, or if you want to, you can put like a little additional statement here. You know, so f is 1-to-1. Okay, that's it. Okay, so now let's do part B, prove that f is onto. So this is a little more challenging, I think. So what you want to do is let little y be in the codomain, which in this case is the real numbers. And then your goal is to show that there exists some little x in the domain, which again is the real numbers, such that if we plug little x into the function, we get little y. So this is a little bit challenging because you have to find x in terms of y. And so you're going to need to do some scratch work. And I will caution you that this scratch work is not part of the proof. It's just scratch work. It's like on a separate sheet of paper. So what I'm going to do is I'm going to put a little cloud. Those of you that have had me before as a professor know I like little clouds. And I'm going to put my scratch work over here just to visually distinguish it from the proof. So what I need to do is actually solve for what x would produce y. Okay? So we want x such that f of x equals y. So, well, what does that tell me? So what I need is that 2x cubed plus 1 equals y. And now what I'm going to do is I'm just going to solve for x. Okay? So I'm going to subtract 1 from both sides. Then I'm going to divide both sides by 2. So x cubed equals y minus 1 over 2. And then I'm going to take the cube root of both sides. So x is going to be the cube root of y minus 1 over 2. Okay, so that's the x that would give me y as an output. And now what I'm going to do is I'm going to go back to my proof and I'm going to whip out that x just like magic, and I'm going to show that that x actually gives me y as an output. So I'm going to say let x equal cube root of y minus 1 over 2. Now if somebody was reading this proof and you had deleted your scratch work, they would be like, wow, where did x come from? That's magic. This is really common in math, actually, that somebody will just like pull out a definition of some letter out of nowhere, apparently, and then it somehow makes everything magically work out. And it's just because people delete their scratch work. There's not like a huge mystery to it. Mathematicians are not like magical geniuses or anything. We just do a lot of scratch work and then kind of throw our scratch work away. Okay, so let x equal this thingy. So then I need to argue that x is actually going to be in the real numbers. And you can just say that x is going to be in the real numbers because y was in the real numbers, and then x is defined in terms of y. That's fine. Okay, so x is a real number as well, and when we plug in x to the f function, we get, let's see what we get. So we get 2x cubed plus 1, and then I'm plugging in for x that weird thing that is the formula for x. Oops, that's a cube root there. Okay, and then I'm just going to simplify this. So this is going to be 2 times, so the cube and the cube root cancel. And then the multiplication by 2 and division by 2 cancel. And then minus 1 and plus 1 cancel. Okay, and you are done. If you want to finish up, you can put, so little f is 1, 2, or you can leave that out. It's up to you. That's it. Okay, so here is a homework problem for you. Go ahead and pause the video and do this one, and then the solution is up on a PDF on Blackboard on today's post. Okay, so let's do another example. I'm going to do another proof that a function is one-to-one, and then I'm going to also prove that a function is not onto. So this will be, I think, the first time you're seeing that type of proof. Okay, so first, let's do part A, which is to prove that G is one-to-one. So we'll do it exactly like before. So I'm going to let x1 and x2 be elements of the domain, which this time is z, or the integers. And I'm going to suppose that these two elements produce the same output. Okay, and then my goal is to show that x1 equals x2. And again, I'm putting this in brackets because that's an optional statement. You don't have to state that. Sometimes it helps you to keep yourself on task by putting these kind of goal statements, but it's up to you. Okay, so we're going to use the fact that g of x1 equals g of x2. You always use whatever you supposed. Try to milk the information out of it. So that means, and now I'm going to use the formula for g. So that means that 3 times x1 plus 1 equals 3 times x2 plus 1. And then I'm just going to simplify, and then finally I get x1 equals x2. So at this point I'm done. Okay, so that's pretty straightforward. Let's do the other part. Okay, so for the second part, proving that G is not onto, so what you have to do is the following. We will show there is some element of the codomain such that g of x does not equal y, so y is not produced by g of x for any, or rather for all, elements in the domain, which again is z. So this is our goal. We want to find some element in the codomain that is never produced by inputting anything from the domain. So in this case, the reason this is true is because we're using the integers. So if you think about the integers, just putting in integers here, then this whole thing right here is going to be a multiple of 3. So 3x will always be a multiple of 3. And it is not possible to write every integer as a multiple of 3 plus 1. So you just have to think of something that you cannot write as one more than a multiple of 3. So something that is one more than a multiple of 3 would be like 4, for example. So you just have to pick something else, like 5. 5 is not one more than a multiple of 3, okay? So let's go ahead and just pick 5, and you can do it with another number, just whichever one you want. And then what we're going to do is we're going to show that the supposition, so suppose there is some x in the domain such that g of x equals y, we're going to show that that leads to a contradiction. So once we get a contradiction from that, that will mean that the supposition was incorrect. So that would mean there is no x in the domain such that it produces y. Okay, so suppose that g of x equals y, then since g of x equals y, that means, so just plug in what g of x is, so 3x plus 1, and then plug in what y is, equals 5. Okay, and then just pursue this equation, simplify it until you get a contradiction. So that would mean I can subtract 1 from both sides, so I get 3x equals 4. And so let's see, if I divide both sides by 3, I get x equals 4/3. Okay, that's our contradiction right there, because that's not an integer. So that would imply that x is not an integer, which is a contradiction. So that tells me there does not exist, or there is no x in the domain such that g of x equals y. And remember y was 5. So g is not onto. Okay, and these last two statements here, that's kind of optional. All right. So here is your second homework problem. That's, again, it's a made-up problem, so the solutions are on Blackboard. Go ahead and try this. Pause the video. Okay, so let's show that h is not 1-to-1. So what I need to do here in this proof, what my goal is we will show there exist two elements in the domain, so x1 and x2 in the domain, the real numbers, such that x1 and x2 are different elements and they produce the same output. So that is how you show that something is not 1-to-1. Okay, so how do you actually find two elements like that? Well, you're really going to need to look at the graph of the function, unless you can just think of them off the top of your head. The graph is what is going to help you. So let me put a little cloud over here for scratch work. So in my scratch work, I'm going to look at the graph of the function, and you can go to desmos.com or use your graphing calculator or whatever you like. I know what this one looks like pretty well from memory. So it's just a parabola that's been shifted up, so that crosses the y-axis at 1. So I just need to find a y value that I think has two different x values that go with it. So like up here, for example, at y equals, I don't know, like at y equals 3, or anything greater than 1, really. I think there are two x values. So now what I want to do is find x values that give y equals 3. So I'm just going to have to solve the equation with 3 in place of y. So let's just do that. So 3 equals 2x squared plus 1. If I subtract 1 from both sides, if I divide by 2, then I get 1 equals x squared. Okay, and then when you do the square root, you can get the positive or negative square root. So I get that x equals plus or minus 1. Okay, so that's all scratch work. And then going back to my proof, So we're trying to show there exist x1 and x2 in the reals such that x1 does not equal x2 and h of x1 does equal h of x2. So I have those now, so I'm just going to define what they are. So let x1 equal -1 and x2 equal 1. Then they are both in the real numbers, and they are not the same. That's pretty obvious, but I'm just going to state it. Okay, and then lastly, I just need to show that x1 and x2 do produce the same value from h. So h of x1 equals, so I'm just going to plug in x1. And h of x2 so h of x1 does equal h of x2. So h is not 1-to-1. That's it. Okay, so let's go ahead and do part B. So for part B, proof. So what we're trying to do here is we will show there is some y in the codomain, which is the real numbers, such that h of x does not equal y for all x in the domain, which is the real numbers. So that's our goal. And what we need to do is actually find a y like that. And hopefully you can see when you look at the formula for h of x that it always only produces positive numbers. In fact, it only produces numbers that are 1 or greater. So any number less than 1 cannot be produced by this function. So you just need to pick a y that is not going to be output by your function. So I'm just going to let y equal 0, which is in the real numbers, so that is in the codomain. And then what I'm going to do is suppose there is x in the domain, which is the real numbers, such that h of x equals y, and then we will show this leads to a contradiction. Okay, so how does it lead to a contradiction? Let's figure it out. So since h of x equals y, that means, so now let's just use the formula. So that means 2x squared plus 1 equals 0. All right, then 2x squared equals -1, x squared equals -1/2. This is a contradiction because any real number squared cannot be negative. Okay, so since we got a contradiction, our supposition was wrong. Meaning there is no x in the reals such that h of x equals y. So h is not onto. And let's see, these statements here, these would be optional. That's it. Okay, so here is your third homework problem, And again, the solutions are on Blackboard, so go ahead and pause the video and try this. Okay, so now that we've finished with proofs of things being one-to-one or not one-to-one, onto or not onto, let's talk about the next concept. A one-to-one correspondence, or a bijection from a set x to a set y, is a function f from x to y that is both one-to-one and onto. So when your function is both one-to-one and onto, it is called a one-to-one correspondence. And here is a little picture of an example of a one-to-one correspondence. So what you'll notice when you have a one-to-one correspondence is that every element in the domain is paired with one element in the codomain, and vice versa. So there really is like literally a one-to-one correspondence between elements in the domain and in the codomain. So you never have two arrows going to the same output, and you will definitely cover all of the outputs or all of the elements in the codomain. Okay, and then the next definition is inverse functions. So suppose that f from x to y is a one-to-one correspondence, so it is both one-to-one and onto. Then there is a function f inverse from y to x that is defined as follows. So given any element little y in big Y, f inverse of little y equals the unique element little x in big X such that f of x equals y. And to say it symbolically, f inverse of y equals x if and only if y equals f of x. So this is exactly the same definition for an inverse function that you're familiar with before. The only thing I would say that's a little bit different from previous definitions that you might have encountered of inverse functions is that previously you probably did not require that f actually be onto. So it's always the case that you needed this one-to-one. And you might have used a test called like the horizontal line test to check for that. I know I went over that when I taught calculus, but onto this might be a little bit of a new condition for you to think about when finding an inverse function. So the reason that you need actually the function to be onto is because for this definition of an inverse function, we're using y as the domain of the inverse. So you need f to be onto in order to have y be the domain of f inverse. Okay, because if f was not onto, then there would be some elements that f inverse would not map to anything. Okay, so if f was not onto, there would be some elements in y that would have nowhere to go under the inverse. I hope that makes sense to you. Okay, so let's do some examples based on inverses. Okay, so in this example, I have a function that is a one-to-one correspondence, and they want me to draw the inverse function. So this is pretty simple. I'm just going to reverse the order of the domain and the codomain. So I'm going to draw y on the left, and y is going to be 5 elements, which are s, t, u, v, and w. And then on the right, I'm going to draw x, which is A, B, C, D, and E. Okay, and then for the arrows, I'm just reversing all of them. So previously I had that A went to T. So now I'm going to have that T goes to A. And then before I had that B went to W. And now I'm going to have that W goes to B. Okay, so before C went to S, and now S goes to C. Previously D went to U, and now U is going to go to D. And then E went to V, and V is going to go to E. Okay, and that's it. Okay, so here's your homework problem. It's almost the exact same as the last one, so go ahead and pause the video, try this, and the solution is in the back of your textbook. Okay, so now let's just review how to find the inverse formula for a function. So this should be something that you already learned in pre-calculus or calculus, but I'm just going to review it here for you. So let me put a little example. Let's say f of x equals 2x plus 1. So step one is you write down y equals, and then you put the formula for the function. So here this would be y equals 2x plus 1. And then you swap the letters x and y. So I would get x equals 2y plus 1. And then you solve for y as a function of x. So let's see, I'll subtract 1 from both sides. And then I'll divide by 2. So I would get, let's see, x minus 1 over 2 equals y. Okay, so I've solved for y. And then finally, the solution that you get for y, that is the formula for f inverse of x. So you can just write that, f inverse of x equals x minus 1 over 2. Okay. Okay, so and this one, this is an example that I made up to go with the ones that I made up previously. So which of the functions f, g, or h from the made up examples are one-to-one correspondences? And for those that are one-to-one correspondences, find the formula for the inverse function. So I hope you remember from these examples that f was the only one that was both one-to-one and onto. So that is going to be f is the only one-to-one correspondence. Okay, and then we're going to find the formula for f inverse. So I'm just going to follow those 4 steps. So first I'm going to write y equals 2x cubed plus 1. And then I'm going to swap x and y. So I'm going to get x equals 2y cubed plus 1. And then I'm going to solve for y. So let's see, I'll subtract 1 from both sides. And then I'll divide both sides by 2. So I get x minus 1 over 2 equals y cubed. And then I'll take the cube root of both sides. So I get cube root of x minus 1 over 2 equals y. And then finally, that is the formula for f inverse. So f inverse of x equals cube root x minus 1 over 2. And that is the formula for f inverse. Okay, so here is a made-up problem to go with the 3 problems that you had previously. So figure out which of these are one-to-one correspondences, and then find the inverse functions. Okay, so the last thing in this section is just a simple fact for you. If you have sets x and y, and you have a function f from x to y that is both one-to-one and onto, then the inverse function will also be one-to-one and onto. Okay, and now let's do section 7.3, composition of functions. So I think you should already know how to compose functions from a previous class, either pre-calc or calc 1. So I'm not going to spend too much time on this, but let's just go over it briefly. Okay, so here is our definition for a function composition. So let's suppose that we have a function f from x to y prime, and then we have another function g from y to z. And let those have the property that the range of f is a subset of the domain of g. So you do need that property in order to compose f and g. And then we can define a new function, g composed with f. So you read the little circle as composed with. So g composed with f is a function from x to z. So it's from the domain of f to the codomain of g. And then the way you evaluate this function is g composed with f of x is just simply g of f of x. Okay? And then that's for all x in the domain capital X. Now the author here says you read this g circle f. Personally, I've never heard it read that way. I've always read it as composed with. Okay, or when you have it in parentheses like this, you read that as g of f of x. And then that function g composed with f is called the composition of f and g. So schematically here we have the domain of f is capital X here, and then the first function that's applied is little f, and little f takes elements in capital X to y prime, okay, because y prime is the codomain of the function f, and then y prime is a subset of big Y, capital Y, which is the domain of G. So then you can take elements from y prime, which is in Y, and using G, you can then map them over to the codomain of G, which is Z. So if you think of the composition as being like a shortcut of that process, it takes you through both of those functions. So you go from little x to f of x, and then from f of x to g of f of x, and then the composition function just kind of shortcuts that and goes straight from x to z. Okay, so let's do some examples. Okay, so here is an example where we have f and g, and then those are given by arrow diagrams, and here all the domains and the codomains are the same, just big X. And they want us to find g of f. I think this is a typo, it's supposed to be little g of little f, and then f of g, and then determine whether those are the same or not. Okay, so let's do this. So we're going to shorten up and just go from x to x by, first I'm going to do g of f. So let me label my elements here. So I have 1, 3, 5, and 1, 3, 5. Okay, so first I want to do g of f. So let me just make some notes over here. So I want g of f of 1. I want g of f of 2. Oops, not 2, 3. And then I want g of f of 5. So let me just figure out what these are. So to evaluate g of f of 1, first I do f of 1. So that's going to take me from 1 to 3. So this will be g of 3. And then I do g of 3, and g of 3 goes from 3 to 1. So I get 1. Okay, so then on my diagram, my arrow diagram of g of f, I go from 1 to 1. Okay, now for the next one, g of f of 3. So first I evaluate f of 3, which is 1. And then I do g of 1, which is also 1. So for my arrow diagram, g of f of 3 goes to 1. And then for the last one here, g of f of 5. So f of 5 is 5. And then g of 5 is 1. So on my arrow diagram, I go from 5 to 1. Okay? Now let's do the same thing for f of g. So I'll do it over here. So this is going to be x again, 1, 3, 5. And this will be x again, 1, 3, 5. And then I'm going to do f of g, or f composed with g. And I'll just make my little notes over here. So I'm doing f of g of 1, f of g of 3, and f of g of 5. Okay, so first let's evaluate g of 1. So g of 1 is, maybe let me do this in a different color. Okay, so g of 1 is 1, and then f of 1 is 3. So f of g of 1 is going to take me from 1 to 3. Okay, and then for the second one here, I'll do g of 3 first. So g of 3 is 1, and then f of 1 is still 3. So for f of g, I go from 3 to 3. And then f of g of 5, first I'm going to evaluate g of 5, which is 1 again. And then f of 1 is still 3. So I go from 5 to 3. Okay, so as you can see, f of g does not equal g of f, because they do not all map. So the image of 1, 3, and 5 is different in those two compositions. Okay. Okay, so here is another problem that is extremely similar, and it has the same typo here. So this is supposed to be g, and little f, and this is supposed to be little g and little f. So go ahead and try that one, and the answer is in the back of the textbook. Okay, so now let's try a composition example where the formulas are actually given by, or where we actually have formulas instead of arrow diagrams. Okay, so first I'm going to find the formula for g of f and then for f of g and then compare them. Okay, so let's start with, you go back to red. Okay, so let's start with g of f. So I want to evaluate g of f of x. That simply equals g of f of x, like this. And so I'm just going to plug in, starting in the inside of the parentheses. This is going to be x to the fifth. That's the formula for f of x. And then I'm going to plug x to the fifth into the formula for g. So this is going to be x to the fifth to the 1/5. And then hopefully you remember that when you have an exponent and then you raise that whole thing to another exponent, that the exponents multiply. Okay, so this is going to be x to the 5 times 1/5. And then that's just going to be x to the 1, or just x. And now let's do it the other way around. So f of g, can write it like this. And so first I'm going to plug in the formula for g of x, which is x to the 1/5. And then I'm going to plug that into the formula for f, which means I'm going to raise it to the 5th. Okay, and then I apply the same rule here. This is 1/5 times 5. So this is going to be x to the 1, which is x. So in this case, g of f does equal f of g. Okay, so let's look at your next example. So this is another composition, and the formulas here are for h and k. So they're just asking me to evaluate 4 different elements here. So let's just go ahead and do that. So I'm going to do k of h of 0, which I can write like this. So first I just have to evaluate h of 0. So that is going to be 6 times 0. Okay, so this is going to be k of 0. And now I'm just going to plug that into the formula for k. So this will be 0 mod 4. Remember, mod 4 means this is asking you for the remainder when you divide 0 by 4 using long division. So when you do that, you're not going to get anything other than 0. Okay. And so let's do the second one. So k of h of 1 is k of h of 1. So this is k of 6 times 1, which is k of 6. And then I want 6 mod 4. Sorry if you heard some sneezing, that's my cat. Okay, so the remainder, when we do long division of 6 divided by 4, you're going to get a remainder of 2. And now I'm going to do k of h of 2, same way. So this time when I do 12 mod 4, the remainder of dividing 12 by 4 is going to be 0, because 4 goes into 12 exactly. And then finally for 3, times 3 is 18, and when I divide 18 by 4, it goes in 4 times, which makes 16, and then you're going to have that remainder of 2 from 16 to 18. Okay, that's it. Okay, so this is your homework problem, and it's 2 problems that are very similar to the last 2 problems that I just did as examples. So go ahead and give this a try. Okay, now let's talk about composing a function with its inverse. So if you have a function little f from x to y that is 1 to 1 and onto, then its inverse function is going to be f inverse from y to x. And when you compose those two functions together in either order, so if you do f inverse of x, then what you get here, this is the identity function on x. So in other words, this is the function that when you plug in something from x, it just outputs that same element in x. And then if you compose the function and its inverse the other way around, this is the identity function on y. So it's the function where when you plug in something from y, it just gives you back that same element from y. So this is what's supposed to happen when you plug a function into its inverse. And if you want to check that a function is the inverse of another function, then what you have to do is do function composition in both orders and make sure you get the identity function in both orders. Okay, so let's go ahead and do this example where we check that these two functions are really the inverse of each other. Okay, so we're going to compose them in both orders and make sure that we get the identity function both times. Okay, so first let's do g composed with g inverse in this order. Okay, so I'm going to do g of g inverse of x. And so I'm going to get, so first I plug in g inverse, and that's square root of x. And then I plug square root of x into the formula for g, which will mean I'm squaring it. Okay, so here I am squaring the square root, so that should always give me just x again. So that's good. I got the identity function. So this is the identity function for the positive real numbers. Okay, and now let's try plugging in the other order. So g inverse of g of x. So first I'm going to plug in the formula for g, which is x squared, and then I'm going to put that into the formula for g inverse. So I have the square root of x squared. Now, if any of you previously had me for calculus, you know that I repeatedly, as often as I possibly could, would mention the following fact, which is that actually the square root of x squared does not equal x, but rather the square root of x squared is the absolute value of x. And that's because if you think about putting any number into the square root of x squared, if you put in a positive number for x, then you get x back. But if you put in a negative number for x, then you get the positive version of that back. Because the first thing that happens is you square x, so that makes it positive. Okay, and then the square root of anything is always positive. So this is the absolute value of x. So what's happening here? Are we getting x? Well, actually, because we're only considering x's that are in r squared, or sorry, that are in r plus, so positive, that means x is greater than 0. So that means that the absolute value of x would equal x in this case, only because we're looking at positive numbers. So we do get that the square root of x squared is x in this case, but only because we were looking at r plus, in other words, the positive real numbers. Otherwise, this would not work. Okay, so in this case, we do get x, which is the, again, that's also the identity function for r plus, the positive real numbers. Okay, so here's your homework problem, and you won't have to worry about any absolute values or anything because these are just linear functions. So give this a try and check the solution. Okay, so now let's talk about section 7.4. So this section actually contains some of the most interesting material in the entire textbook, in my opinion. So it's cardinality with applications to computability. So let's talk about cardinality for a second. I can't remember honestly whether we had talked about this before or not, but the cardinality of a set A is just simply the number of elements that are in A. So for example, if we want the cardinality of the set containing 4, 5, 6, it's written like this. You just write it with these little, it's like an absolute value sign. So whenever you encounter something that looks like the absolute value in math, this notation right here, it always refers to some type of measurement of size. and that could be different in different contexts. So for the absolute value, you're measuring the size of the number in the sense of how large it would be if you didn't care about the sign. And in this case, for cardinality, you're measuring the size of the set in the sense of the number of elements that are in it. So that little double line thing, it always refers to size. And I think the inspiration from it actually comes from like architectural drawings where you use this type of little little symbol to measure the size of different widths and lengths. Okay, so anyway, the cardinality is the number of elements in the set. So for example, the cardinality of the set containing 4, 5, 6 is 3, and then the cardinality of the set containing 4, 5, 6, 7 is 4. And then if you have a set that's infinite, then the cardinality is infinite. But one of the most interesting facts in all of math is that there are actually different kinds of infinity. Different kinds of infinity. So what could possibly be meant by that? So to explore this concept, we're going to need a more formal definition of cardinality. And if you think this is interesting, then I invite you to check out a book called Beyond Infinity, An Expedition to the Outer Limits of Mathematics, which is one of the journal readings that's up on Blackboard. Okay, so here is our more formal definition of cardinality, and we need this definition in order to explore the concept that there are different kinds of infinities. So let A and B be any sets. Then we say that A has the same cardinality as B if and only if there is a one-to-one correspondence from A to B. In other words, A has the same cardinality as B if and only if there is a function f from A to B that is both one-to-one and onto. Okay, so this is interesting, and we can think about, for example, just a small example here, if we have a set 1, 2, 3, 4, that has the same cardinality as A, B, C, D. Well, we can see that they both have 4 elements, so we know they have the same cardinality for that reason. But we could also think of making a one-to-one correspondence from one to the other. For example, I can make a function from f, or a function called f from 1, 2, 3, 4 to A, B, C, D, given by the following rule. So f of 1 equals A, f of 2 equals B, f of 3 equals C, and f of 4 equals D. And if you think about it, the concept of set cardinality is actually a deeper concept than the concept of numbers, rather. There was a time in your life when you didn't know what a number was, and somebody had to teach you what they were. So how did they do that? Do you remember how they did that? So I think for me, I remember doing it on my fingers, right? So if you think about counting on your fingers, you have a little hand here, and this is 1, 2, 3, 4, 5. And what you're doing when you're counting on your fingers is you're making a one-to-one correspondence between the set that is your fingers and the set that is 1, 2, 3, 4, 5. Because, you know, you have thumb. I can't spell thumb. You have your thumb. You have your index, middle, ring, and pinky. And then you're making a one-to-one correspondence with the set 1, 2, 3, 4, 5. This is the one-to-one correspondence. You're making these numbers correspond to your fingers. And you could give that function a name, like f or something. Okay, so let's see what we can do with this concept. Okay, let's look at an example where we apply this new definition of cardinality. So let 2z be the set of all even integers. So in other words, 2z is this. It's ... -4, -2, 0, 2, 4, and so on, like that. So going off infinitely in both directions. We want to prove that 2z and z have the same cardinality. So this is a little bit strange, actually, because if you think about it, the even integers are a proper subset of the integers. So in other words, the even integers are inside of the integers, but there are lots of other things that are not in the even integers, like all of these odd numbers are not in there, and yet somehow the integers have the same cardinality as the even integers. Even though the even integers, they're a subset of the integers, but they don't include all of the integers. So that's really kind of strange. But let's go ahead and do this. And so what happens is that when you define cardinality in this new and kind of unusual way, you do get these strange consequences like this. So let's go ahead and try this and see that this is the case. So what I'm going to do is I'm just going to list out the integers, so just a few of them, and then this continues on in both directions, and then I'm going to list the even integers, so -2, -4, so this is z, and this is 2z, and then I'm going to let my correspondence work in just the most kind of obvious way, so I'm going to assign it like this. So this is like my little arrow diagram here. I've just done it sideways. So what I'm going to use for my formula here, I'm going to go from the integers to the even integers, and then my formula is going to be defined by, oops, this should have just been, sorry, I'm going to get my little eraser out. Okay, so this should have just been f here. So the formula is going to be just 2x. So I'm just doubling the inputs, and then that'll always give me an even number as an output. Then f is in fact 1-to-1 and onto. 1-to-1 and onto. I'm not going to go through the proof of the fact that it's 1-to-1 and onto, but I think it's not too hard to see that from my little arrow diagram. So every input, every integer will be having a different output, and then every possible output in the codomain will have some input that produces it. Okay, so now let's think about the concept of countable versus uncountable. So a set is called countably infinite if and only if it has the same cardinality as the set of positive integers z+. A set is called countable if and only if it is finite or countably infinite. A set that is not countable is called uncountable. Okay, so we can think about countable as meaning that you can put your set into a 1-to-1 correspondence with either the positive integers or with some subset of the positive integers. But there's an alternative way that I want to think about this, and that is really just to do with counting itself. So a set is countable if and only if we can list the elements in some order. It doesn't really matter what order, just in a systematic way. And our list will eventually cover every element of the set. So we can list all the elements starting somewhere, and then we can go on for as long as we want. Our list can be infinite, but it can only be infinite in one direction. So it can't go in both directions like the integers. It has to only be infinite in one direction, just like the positive integers, because that's what we're really doing here. When you make a list of your elements in your set, what you're really doing is placing them into a 1-to-1 correspondence with the positive integers, where the first item in your list goes with 1. And then your second item in your list goes with 2, and then so on and so forth. The third goes with 3. And so on and so forth. Okay, so what you're really doing is producing a 1-to-1 correspondence. So this produces a 1-to-1 correspondence between your list elements and the positive integers. Okay, so this is the positive integers here. All right, so that's how I want us to think of what it means to be countable, is you can list all of the elements starting with 1 and then going to 2, 3, 4, etc. You can make a list like that that will eventually cover every element of your set, and you can keep listing forever, but only in one direction. Okay, so now let us try showing that the set Z of all integers is countable. So we know how to make a list of all the integers. Just by writing them all out like this. So -2, -1, 0, 1, 2. But the problem is this list continues infinitely in both directions. So in this type of list, you would not have placed it then into a one-to-one correspondence with the positive integers. So we need a list that just goes in one direction. Okay, so let me show you a way that you can actually list all of the integers, and then your list will only be infinite in one direction. So the first thing in the list is going to be 0. The second thing in the list is going to be 1. The third thing in the list is going to be -1. Fourth thing in the list is going to be 2. Fifth thing in the list is going to be -2. Sixth thing in the list is going to be 3. Seventh thing in the list is going to be -3. And then it's going to continue like this. So this list will eventually reach every integer. If you're an integer and you're waiting to be listed, you can figure out exactly how long it's going to take you to be listed. Say I'm integer -189, I can figure out exactly how long it's going to take me to get on that list. The list will eventually reach me. So there aren't going to be integers that are going to be skipped at all. Okay, so this is our one-to-one correspondence with the positive integers. So on this side, these little list items here, the number on the list, this is z plus. And then over on this side, the things that we're listing is z. Okay, so that is this example. Okay, so now let's look at a little more challenging example. So we need to show that the set Q plus of all positive rational numbers is countable. So remember, rational means that you can write it as the ratio of an integer over an integer. Okay, so it's all fractions of where the top and the bottom are both positive integers. So this is a lot trickier to do. So let me try showing you why this is so tricky. So a first attempt might be something like the following. So maybe I could start with listing like 1/1, and then number 2 could be like 1/2, and 3 could be 1/3, and then 4 could be 1/4. But this won't work because this pattern would never reach certain rational numbers. So for example, it would never reach 2/3 because all of the numerators in that list are 1. So that won't work. So let me try something else. So maybe a second attempt, maybe instead of changing the bottom each time, maybe I'll change the top each time. So I could do like 1/1, 2/1, 3/1, but this has the same problem. So that's not going to work either. So somehow you've got to devise a way that you're going to reach each and every single rational number. So what would really help is if we had a way to write out all of the rational numbers, like to make a complete comprehensive set of the rational numbers, a picture of it. So let me show you a way that you can actually do that. So I can draw Q plus like this. Here's a little diagram. So on the top row, I'm going to do 1/1, I'm going to do 1/2, 1/3, 1/4, and so on. And then on the next row, I'm going to do 2/1, 2/2, 2/3, 2/4. And then on the third row, 3/1, 3/3, 3/, oops, that should have been 3/2, and then 3/3, 3/4, and so on. And then on the next row, 4/1, 4/2, 4/3, and then 4/4. And so if I just keep going like this, I can draw every single rational number in this grid here. Okay, so now what I want to do is I want to figure out a way to convert this into an ordered list. So what I'm going to do is actually pretty clever, and I don't know who first thought of this, but it is really clever. Okay, so the way I'm going to list all of these elements is I'm going to let 1 over 1 just be the first one, and then I'm going to go down to the second one here. So 2 over 1 is the second one, and then I'm going to go up along this diagonal here and let 1 over 2 be my third number. And then I'm going to go to the right, and this 1/3, that'll be my fourth number. And then I'm going to go back down along the diagonal. But when I get to 2 over 2, I've actually seen that rational number before. It was 1 over 1, so I'm going to skip that one. And I'm going to go straight on to 3 over 1, so that'll be my fifth number. Okay, and then I'm going to go down to 4 over 1, and that'll be my sixth number. And then I'm going to go back up along the diagonal. 3 over 2 will be my seventh. And then 2 over 3, that'll be my eighth entry on my list. And then back up to 1 over 4, that'll be the ninth one. And then I'm just going to keep going like this. I'm going to go over, down, 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 and then, oops, down, and then back and forth like this. And then whenever I come to one that I've actually seen before in a less reduced fashion, like 2 over 4 is the same as 1 over 2, I'm just going to skip it. 3 over 3 is the same as 1 over 1. 4 over 2 is the same as 2 over 1. Okay, I hope this makes sense to you guys. So my list that I end up getting is like this. It's 1 is 1 over 1, 2 is 2 over 1, 3 is, where did I put it? 1 over 2, 4 is 1 over 3, and etc. And I hope you can see that by doing it in this fashion, I will eventually reach every rational number. Okay, so now we're going to go over one of the most celebrated results in all of mathematics, and this was devised by Cantor, this particular proof, which shows that the set of all real numbers between 0 and 1 is uncountable. So this is really classic proof that everyone who studies higher math should study. So I hope you're still watching this video. Okay, so what we're going to do is by contradiction. So we're going to suppose this set is countable. Then if it is countable, we can make a list. Make a list of all the elements. Just abbreviate elements like that. Okay, so suppose this is our list, where every number is written in decimal form. Okay, so since they're all between 0 and 1, they're all going to start with 0 point something, 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 something. Okay, so suppose the first element is 0 point A1, A2, A3, A4, dot, 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 like that. Okay, and suppose the second element is 0 point B1, B2, B3, B4, dot, dot, dot. And then suppose the third element is 0 point C1, C2, C3, C4, dot, dot, dot. And suppose the fourth element, so it goes on like this. I think you see what I'm doing. I mean, I'm going to run out of letters eventually, but I can just start numbering them after that or something. Okay, so this is going to go on like this. Okay, so then what we want to do is find a contradiction. So we're going to find a contradiction. Okay, so I'm going to define a number called x. So define x to be 0 point, let me call it something else like alpha. So 0 point alpha 1, alpha 2, alpha 3, alpha 4, and so on and so forth, where we choose the alphas in the following manner. So where each alpha I is chosen as follows. Okay, so alpha 1 is chosen to be different from A1, alpha 2 is chosen to be different from B2, alpha 3 is chosen to be different from C3, and alpha 4 is chosen to be different from D4, etc. Okay, so etc. for all I equals 1, 2, 3, and continuing infinitely. So every single digit of x is chosen so that it's different from one of these numbers on the list. Okay, so you look at this diagonal here, this A1, B2, C3, and then D4, and then you choose alpha's digits in such a way that alpha 1 is different from this one, and alpha 2 is different from this one, and alpha 3 is different from this one, alpha 4 is different from this one, and just so on and so forth forever. Okay, and so then what you can say is that then x is not on the list. And how do you know that x, this number x with all the alpha digits that we just invented, is not on the list? Because x is different from every number on the list in at least one digit. Okay, but x does have to be a real number, and x does have to be between 0 and 1. Oops. Because every number of the form 0.alpha 1, alpha 2, alpha 3, etc. for alpha I in the set 0, 1, 2, 8, 9 must be a real number. So we defined x in such a way that it does have to be a real number. We gave it a decimal form, and anything in a decimal form is a real number. And since we made it start with 0, it has to be between 0 and 1 inclusive. So x does have to be a real number, but we've shown that x is not on the list. X can't be on the list because we defined it in such a way that it would be different from every single number on the list. So this is a contradiction. So I'll just kind of squeeze that in the corner here. Contradiction. So it must not be possible to list the real numbers. And so at least the real numbers between 0 and 1. And so because of that, the real numbers between 0 and 1 are uncountable, and that in fact means that the real numbers as a whole, including other things less than 0 and greater than 1, are also uncountable. So that is a really, really interesting and celebrated result. Person who thought of this was quite a genius, good old Cantor. And if you want to read more about Cantor, I believe his story is somewhat included in the book called Logicomics, which is one of the journal readings. All right, so thank you for watching the whole video. Sorry this ran over a little bit, but there are not going to be any homework problems from this section. It's just a matter of interest and edification. So thanks for watching, everybody, and I'll see you next time.